So with that, I'll introduce our next speaker, Professor Maria Konsta of University of Texas, Arlington.
Excellent. Thank you, Shiho. Good afternoon, everyone, again. My name is Maria Konsta, and greetings from the University of Texas at Arlington and the Center for Advanced Construction Materials. We have a lovely weather here, really nice, though the temperature is a little bit low, but I like it. It reminds me of my other hometown, Chicago, and I believe that we are much better now than Chicago. I mean, I don't know what Professor Shah is telling us. So I would like to talk today about the relationship between the carbon nanotube dispersion state, electrochemical impedance and capacitance, and mechanical properties of percolative nano-reinforced mortars. Carbon nanotubes, we all know that they exhibit remarkable intrinsic properties, including strength, stiffness, electrical conductivity, and it was long shown that depending on their geometrical characteristics, aspect ratio, and morphology, low carbon nanotube concentration levels in cementitious materials allow electrical conductivity and impart enhanced mechanical and durability properties, also as an added bonus sensing ability. So in the light of the fact that the homogeneous distribution of individual nanotubes in all matrices, but especially in the heterogeneous cementitious matrices, plays a crucial role to such enhancements, the characterization of the degree of carbon nanotube dispersion is of great importance. Unfortunately, carbon nanotubes are highly hydrophobic. The dispersion process of nanoscale carbon fibers, including nanotubes, carbon nanofibers, starts with the disentanglement of CNT and CNF agglomerates. Ultrasonication is a great method for dispersion, and so far, transmission electron microscopy, scanning electron microscopy, atomic force microscopy have been routinely used to qualitatively characterize the dispersion of CNTs and get great pictures like the ones that I'm showing to you in this slide. Actually, this is the structure that looks like a swan is a beautiful nanotube of a diameter of 20 nanometers found in a pore of a cement base of 18 hours old. So the other methods, such as spectroscopic techniques, including UVVs, ultraviolet visible light, and Raman spectroscopy, can also be used to assess the degree of CNT dispersion in aqueous suspensions. A perfect example is given in this slide, where we can see results of the absorbance of the ultraviolet visible light of a 0.1 carbon nanotube suspension for different sonication energies. So what we observe is that in the beginning and even before sonication, a substantial part of carbon is bound in large particles and actually does not absorb enough light. But as the energy supply increases during the usual course of ultrasonication, then disentanglement occurs and a larger part of a carbon is freed to absorb more light. On a second step, the particle size distributions of the resulting suspensions can be analyzed during a dynamic like scattering tests. In these tests, in DLS tests, we can measure the z-average hydrodynamic particle diameter, which is obtained from the cumulant analysis of the normalized electric field autocorrelation function. And we use the Stokes-Einstein equation with the diffusion coefficient determined from the autocorrelation function. There is a certain probability that the light scattered by larger particles will swamp the light scattered by smaller particles, since the light intensity of a scattered particle is proportional to the diameter in the sixth power. And this means that larger particles are overestimated in these dispersions, and this is why you see the diameter estimated here from these tests. The lowest one was 169.99 meters. So this is the reason, the actual reason, the change of diameter with ultrasonic treatment using DLS actually shows only a trend in the change of particle size. From the figures in our slide, you can observe through though that the dispersions treated for a short ultrasonic time present a bimodal and broad distribution, and this is actually an indication of a heterogeneous particle distribution. But with ultrasonic treatment time, the dispersions get more homogeneous and size distributions are narrowed. And this can also be observed by the information that obtained by DLS called as the polydispersity index, and higher values of the polydispersity index indicate very heterogeneous particles. So you see the values from the S received 1.91, 0.92, etc. And this is indicative of the agglomerates existent in dispersion, and of course a lower degree of dispersion. However, a polydispersity index of about 0.4 and less than 0.4, such as in the case of our well-dispersed mixes, where the ultrasonication energy reaches 3,500 kilojoules, then this shows that particles and agglomerates are more homogeneous in size. Nevertheless, microscopy and spectroscopy techniques can be used to assess the degree of CNT dispersion in aqueous suspensions. They cannot establish a relationship between the state of CNT dispersion and the distribution of individual CNTs within the matrix. And this is actually the key for the enhancement of the mechanical and durability properties of every nanocomposite, and also be able to predict electrical behavior if it is of interest. In this part of the presentation, I will show you results of the effect of the state of nanotube dispersion on the electrochemical impedance response of CNT reinforced mortars, with measurements based on the complex impedance and mainly capacitance. I will not show you many different types of CNTs, because in this work we concentrated on many different proportions of CNTs, ranging from 0.025 and up to 0.5. And we will measure and show you the impedance profiles, so that is the real and imaginary part of impedance, and the capacitance of all proportions of mortars, ranging from 0.025 to 0.5. So the complex impedance of the CNT reinforced mortars can be obtained using an AC signal scanned over frequencies ranging from 20 hertz to 300 kilohertz. The figure shows a typical Nyquist plot of 28-date mortar, which is reinforced with 0.1% CNTs, and the high frequency arc that starts from the 100 kilohertz to 300 kilohertz is associated with the bulk properties of the material. We take two pieces of information: the real part of the impedance, known as resistance, which arises from the intrinsic resistance of nanotubes and depends on the development of a complete nanotube network within the matrix. And it is usually used to determine the critical amount of CNTs required for the formation of a continuous conductive network and providing information on the percolation threshold. For this particular information, we use the frequency of 100 kilohertz, which is also called a cusp point. And this is the point where there is a perfect agreement between the real and the absolute impedance values. And at this point, the material acts as a neat resistor. This means that it does not exhibit any energy storage capacity. And this is the typical approach, a most common technique, which can measure the impedance directly in the frequency domain by applying just a single frequency voltage to the electrodes and measure just the phase shift in amplitude of the real and imaginary impedance at that frequency. So in this figure, you can see the plot of the percolation threshold using the resistance values that we collected through the impedance measurements at the cusp point for 100. The frequency was 100 kilohertz. And from this figure, we can see that the 0.1% per weight of carbon nanotubes is critical to the formation of a complete conductive network into the matrix and defines what we say the onset of percolation threshold. I'm not going to go into details of how we calculated this. I'm showing you both the experimental data and the theoretical calculations, and they do agree with each other very well, but I'm not going to go into details for the resistivity. But what I just want to say that from the complex impedance diagrams of the Nyquist class, we can also observe that there is a frequency of at the frequency of 300 kilohertz, we also obtain other values, which are the values that are called the reactant values. The imaginary part of the Nyquist plot is giving us the reactance values, and these values, as you can see here, actually they increase with the CNT content. The physical meaning of the imaginary part of the reactance is that it represents the energy storage part of the circuit element, because we can model the complex impedance of any nanocomposite as a resistor and a capacitor. From the resistivity reactance plot in this figure, in this slide, we observe that while the nanocomposite's resistivity decreases with the increase of the CNT addition up to 0.15%, there the conductivity reaches a plateau. But however, we observe a different trend for the imaginary part of the impedance, the reactance. For CNT loadings above percolation, while the real part of impedance decreases and conductivity increases due to the established nanotube pathway, the values of the imaginary components of impedance increase with the CNT content. Obviously, it's not possible to achieve perfect dispersion, and therefore some CNT agglomerates always exist, even in the highly dispersed mixes, such as the 0.1%. So the imaginary part of the impedance can be used to evaluate the state of dispersion and assess the existence of the agglomerates in the matrix, And these higher reactance values, therefore, are indicative of a higher electrical energy storage capacity due to the presence of either bigger or more CNT agglomerates that are capable of storing electrical charge. For the characterization of the dispersion degree, it makes sense to use values of capacitance instead of reactance, as the capacitive phase is due to the localized nanotube cementitious material structure, similar to that of a metal insulator, metal capacitor, and it depends on the presence of CNT agglomerates in the matrix. Furthermore, capacitance is associated with interfacial or space charge polarization that occurs when there is an accumulation of charge at an interface between two materials or between two regions within a material. The concept of space charge provides actually a natural bridge between the bulk properties and the properties of any neighboring phase, such as CNTs. So as it can be observed from the resistivity capacitance plot in this slide, when a uniform dispersion of CNTs is achieved in the matrix, there is a consistency between resistive and capacitive phases, and resistivity and reactance and capacitance decrease as the nanotube content increases. With the capacitors connected in parallel, values of both resistivity and capacitance decrease up to 0.1% per weight of cement CNTs, where percolation threshold is established. We can observe that capacitance values of the 0.15, 0.2, 0.3, and 0.5 mortar mixes are up to 5 times higher, respectively. Before I show you my final slide, with the correlation between capacitance and mechanical properties, I just want to point out that the values of the modulus that I'm going to show you here were measured from the 3-point bending tests on 4x4x16 prismatic beams, and the compression tests on the half prisms. Fracture mechanics tests on notched beams at 20 by 20 by 80 millimeters, using both the linear elastic fracture mechanics theory and the 2-parameter fracture model. So all these values of the Young's modulus seem to be in a very good agreement. Now I can move up to my final slide, where I want to show you from the plot in this figure, the modulus capacitance plot. In this figure, there is a very good correlation between the capacitance values and the Young's modulus of the nano-reinforced mortars as a function of the CNT content. The 0.1 per weight of cement carbon nanotube reinforced mortar demonstrates an average modulus of about 27.5 gigapascals, and these values actually correspond to the highest improvement in, not shown here, strength and stiffness, and at the same time the lowest values of the capacitance. So, we cannot ever claim that a perfect dispersion really exists. A few small in size CNT agglomerates that are capable of storing the electrical charge are probably present. Hence, some low values of both capacitance and resistivity are observed. But because these lowest values of the capacitance measured right in the area where the percolation threshold was defined, it is interesting to observe that the 0.1 per weight of cement mortar exhibits low resistivity, the lowest resistivity. It exhibits a low resistivity, but not the lowest. The lowest resistivity is observed in the 0.15% mortar. Then we increase that 157% in capacitance was recorded. But looking at the Young's modulus values, the 0.15% mix compared to the 0.1% CNT reinforced mortar exhibits lower strength and stiffness. And the 0.2, 0.3, and 0.5 mixes resulted in even lower increases of both strength and modulus, and at the same time, modest increases in capacitance value. The trend of the capacitance values observed can correlate well with the observed values for the modulus of elasticity. Therefore, we believe that capacitance values can provide a very good indication of the CNT's state of dispersion inside the cementitious matrix. And with that, I would like to conclude. We can use all the spectroscopic techniques like UVVs and DLS and zeta potential to assess the degree of CNT dispersion in aqueous suspensions. However, these techniques cannot really establish a relationship between the state of CNT dispersions and the distribution of individual CNTs within the matrix. Therefore, we cannot have a correlation between the resulting properties of the cementitious nanocomposites. Capacitance can be used as an indication of the dispersion state of the different amounts of CNTs in cementitious matrix. And from the capacitance-Young's modulus relationship, we can observe, we can have valuable information on how the actual CNT dispersion and the presence of CNT agglomerates affect the mechanical properties of nano-reinforced mortars. Thank you very much for your attention, and please send me any questions, or if we have time for questions, I will be happy to answer.
All right, thank you so much, Maria. But thank you again for that wonderful presentation.
Thank you.